Okay, we're going to continue on. This is Chapter 1, Section 4. And in this chapter, we've taken a look at a variety of different things so far. In this section, we're going to take a look at measurements. Specifically in this section, we're going to talk about the process of measurement, identifying the three basic parts of a quantity, describing the properties in units of length, mass, volume, density, temperature, and time, the SI base units, and some basic unit calculations and conversions in the metric system and other unit systems. And a lot of that we'll be doing in class too, to make sure you got the basics down. Okay, so on the screen here you see the base units of the SI system, and these are things you need to know. The base unit in the SI system, the International System of Units, is the meter for length. For mass, it's the kilogram. Now note that it's not the gram, it's the kilogram, okay? And the units are there to the right, capital K, little g. Then you've got time, which is the second. For electrical current, we don't use that too much in this class. You'll use it in physics and such, but amperes are the units represented by A. For temperature, you're used to Fahrenheit and Celsius, I know, probably a lot in the past, but here we're going to need to use Kelvin. Now, Kelvin's always going to be written out lowercase k, E-L-V-I-N, but the symbol will be noted as a capital K. Notice you don't put a degree symbol in front either. You don't use the naught. So, like with Celsius, you'd put naught, which is that little circle thing, so naught looks like this. And then you write C, that's Celsius, but for Kelvin, we just write K. Okay, there's no naught there. And this thing here is actually, if you didn't know, it's N-A-U-G-H-T, naught. Okay, the degree symbol, in other words. And then for amount of substance, the mole, you should be familiar with that from physical science, and went through a whole lot of rigor to try to reduce that to 3 letters from 4 to save you a whole bunch of time. That was humorous. Luminous intensity, candelas, from candle. And you don't see that too much either. We don't work with that too much in this class. Okay, moving on. Here you've got a list of metric prefixes and symbols, and you can see here the different prefixes and symbols. We are probably going to cut it off around here. I mean, we're certainly going to hit scientific notation with numbers that are, 10 to the, 23rd, 28th, 34th power, significantly higher. But as far as prefixes, if you can focus on getting those down, that would be nice. So deca, hecto, kilo, mega, and giga. 1, 2, 3, 6, and 9 for positive numbers. And then for decimals, numbers less than 1, the ones that we're probably going to see often are these: deci, centi, milli, micro, nano, and pico. Deci, of course, you know, tenth, hundredth, centi, like century, milli for thousandth, like a millennium. And then you start getting into other domains like micrometers, and microscopes. When you start looking at things you can't see with the visible eye, 10 to the negative 6th. Nano, with nanotechnology now we're starting to get down into really small values, 10 to the negative 9th, and then picos, 10 to the negative 12th. Okay, so if you can be familiar with these and these, in other words, know them, that would be very helpful, and it will help make your working class a little bit easier. Okay, so where did all of this come from? Well, around 1799, you had the French Revolution, and one of the situations going on in France, if you remember from your European history class, if you've taken it already, there was a lot of upheaval in Europe at this point in time, particularly in France. There was a lot of starvation. Agriculture was really bad. There was a lot of poor crops year after year, and the people ultimately revolted against the government and the wealth of the aristocrats. But out of this, one of the things that became critically important was trade. Trade needed to be stabilized because France was economically and agriculturally starving to death, and to enhance trade and to stabilize it throughout the region, because every region still was measuring things. People were on the barter system. They would go and say, okay, I want to sell you X number of cows, or there was no method of measuring their weight. There was no equivalency standards. There was no standardized units of length or monies even at that point in time. It's really hard to comprehend because we're so used to having systems like meters and inches and yards and such, but that didn't exist consistently throughout any of the countries in Europe at this point in time. So as a result of the French Revolution, one of the things that came out of it was a attempt to stabilize and standardize units of measure, and that's where we get the international system from, those 7 base units we talked about on a couple of the slides previous. One of the things that comes out of this, really, and you can still see this today if you go to France, is the meter. At this point in time in France, you could go to down the street. If you needed to measure something, you could go, and they had these put into buildings all over Paris, and you can still see them today. Obviously, this is a photograph of one, but this is obviously a meter. Okay, this distance here from here to here. So you could go down the street to the corner, and you could measure something and see what part of a meter it was. You could even see some little demarcation lines in there. And so these were throughout the city of Paris, and these were used to standardize the unit of measurement. And of course, as you know, right after 1799, you had the rise of one of the great conquerors of history. My pen keeps doing that. But you have Napoleon. I guess you can figure out his last name, Bonaparte, the Corsican. And he conquered Europe, 1799. Shortly after that, he came into power really around 1802 to 1815. And when he conquered Europe, he shoved, so to speak, this metric system, this unit of measurement, as well as all the other standardized SI base units, down the throats of all these different countries, because as he conquered Europe, he brought them into the French Empire, and they needed to standardize trade throughout the empire. So he made everybody use his system, and that's why it's become so popular and still predominantly what they use in Europe today. All right, moving on. Now here you see a measuring stick, and you can see you've got meters and yards and centimeters and inches, and what you've got here really is a combination of a couple different units, right? You've got the American system, we call it, it's the United States Customary System, USCS, United States Customary System, and that's where we get things like inches and yards and acres and lots of, gallons and all the different terminology we use in the United States. And we also use metric a bit too. We've tried to convert to metric for quite a bit of time because metric and the SI base system is nice and simple to use because it's very easy to work within, and it's also kind of become the standardized units for science. But think about it. You go to the grocery store, right, and you buy milk, and you buy milk by the gallon. That's United States Customary System, okay? But then you go and you buy Coca-Cola, and that you buy by the liter, which is, an entirely different system. You get metric or SI, okay? And so it's funny, this breakdown here, because milk is local, right? We buy milk from local dairies and stuff. It's considered a local product. We use the US system because that's domestically what we've always done. But because you've got Coca-Cola, which is something of an international product, right? They sell Coca-Cola all over the world. We buy it by the liter, and we don't think about the fact that we're actually buying things in the same store at the same time in our same grocery cart with two different systems to measure fluids. But because Coca-Cola is an international company and they sell Coca-Cola throughout the world, rather than having all different types of units, they just use the most common unit throughout the world, which is metric or SI, and they use liters. So interesting, but still something to pay attention to. Okay, now let's go on. Okay, here's an example of the kilogram. And this is a standardized unit. You can see the kilogram right in here, this piece of metal, and it's within a couple of glass bells. And this is actually a replica. I think this one's here in the United States. It's in Maryland. And the original kilogram, I think it's in the Louvre or it's someplace held up in a vault in France. But it's kind of like what everything gets measured against, and it's the standardized unit, and it's probably been around for a couple hundred years. But it's like the perfect kilogram, and then everything's measured against it. And now one thing I do want to talk about while I get a little room on the screen, when we talk about measurements, there's really three kinds of pieces of information. Three kinds of information or info that you want to get out of a measurement. Okay, so when you talk about a measurement, you're going to talk about the magnitude. And when we talk about magnitude, we're really talking about the number. Okay, so magnitude or number. The second thing you're going to try to get out of it is the unit, right? The unit of measurement you're going to do. So if I say 3 gallons, that's different than 3 liters. So we need to understand what type of unit we're talking about. And then the third thing is we also need to understand what the level of uncertainty in the measurement is. And you may remember in working with, and this comes into play with, rounding, your rounding rules. And we'll review those here shortly. And then also significant figures. I almost said scientific notation. Significant figures. Okay? What numbers matter in a number. So both of these come into play with the uncertainty. And again, there's a variety of rules around those, and we'll review those because I know you probably haven't looked at them too much since you've taken physical science. Now, let's move on. Temperature. Couple things about temperature. When we measure temperature, what are we really doing? Are we looking at how hot or how cold something is? Well, not exactly. What we're really looking at when we measure temperature, we're taking a look at how much heat something contains. How much heat something contains. And you'll learn that heat's often pretty much just a reflection of how much energy something contains. So how much heat something contains. And so we'll look at, when we talk about it in class, we'll take a look at heat from both, or temperature, both from a perspective of energy and also from a perspective of how much heat something contains. So there's really 3 systems, right? You're familiar with Fahrenheit, and you're familiar with Celsius. And then what we use here in science is Kelvin. And it's important because in Fahrenheit, and I'm just going to briefly go over this. Now, if you think about water, water boils at 212 degrees Fahrenheit, right? Water freezes at 32 degrees Fahrenheit. And you get down to 0 degrees Fahrenheit. And you can also have negative temperatures, right? You've probably never been any place where it's been 10 below in Fahrenheit. I have. It's quite cold. But you can have a negative value in Fahrenheit. Okay, and that's going to come into play in a second. So keep that in the back of your head. Now in Celsius, right? 212 Fahrenheit is 100 degrees Celsius. Okay, that's boiling for water. Those two are equivalent. And then you can also, I think 0 degrees Fahrenheit is like 32 degrees Celsius. I'll write that in there. I'm not positive off the top of my head, but I think it's something like that. And then, of course, you can get negative temperatures. You can also get something like negative 10 degrees Celsius, okay? Now, Kelvin. Kelvin is really the same thing as Celsius, except whatever the temperature is in Celsius, you just add 273 to it. So 100 degrees Celsius, you add 273 to it, and that makes it 373 Kelvin. If you had 32 degrees Celsius, you would add 273 to it to convert it to Kelvin, and then it would be 305 Kelvin. And likewise, the opposite direction. If you're going to go from Kelvin to Celsius, you just subtract 273 out. So that's really the difference between Celsius and Kelvin. But the important matter, and remember I said these both can have negative numbers, the important factor and why we use Kelvin for science is because the lowest temperature you can get in Kelvin is 0. Okay, oops, and I remember we don't use we don't use degrees for Kelvin. Zero Kelvin, okay? You cannot get a negative Kelvin value. If you do, you did something wrong in your math, so please double check that. So this is actually a value that is known as absolute zero. And absolute zero represents the temperature, the amount of heat or the amount of energy, or lack thereof, you could say. It's the point at which atoms do not move. They stop moving. Electrons stop orbiting the nucleus, and they just kind of freeze in place. There's no energy, there's no heat, there's no motion, there's no vibration. So that's absolute zero. Things just come to a standstill. And that's the lowest value you can get in Kelvin. So why is this important? Well, if you can have a negative temperature in Fahrenheit and Celsius, the problem comes when you plug a negative number into an equation, it's going to give you a negative value, right? And if you have a positive value, you multiply it by negative 10 degrees Fahrenheit, you're going to get a negative value. And that's going to cause a problem. Same thing with Celsius. Okay, and that's going to give you an error. It's going to give you some number or some value that just doesn't make sense. Whereas in Kelvin, you cannot possibly get a negative value because you can only multiply something by 0, which of course will give you 0, or anything above 0, 1, 2, 3, all the way on up. And if that's the case, you'll always end up with, at worst case scenario, 0 or a positive number. In other words, these are going to accurately reflect the value you're trying to work for. And we'll take a look at that in class. If that's a little bit confusing to you, just mention it and we can walk through that. We'll do a couple scenarios in class and you can see how that pans out. All right, now we're taking a look here at volume. Okay, and take a look at volume here. You've got different dimensions, right? You got cubic meters, cubic decimeters, which is also a liter, cubic centimeters, which are also a milliliter. And this one here, I'm not overly concerned that you remember this one. A cubic decimeter is a liter. A cubic centimeter is a milliliter. Now this one we see it often if you watch hospital shows or like ER or things like that, or Scrubs or whatever. If they say, give somebody, 10 cc's of something. The cc stands for cubic centimeter, or cm cubed, right? Which is what we're looking at here, cm cubed. So 10 cc's, 10 cubic centimeters, that's the same thing as saying 10 milliliters, okay? So if you had a graduated cylinder and you needed to get 15 cc's of something, you would just simply measure, here's 10, here's 20, and this is demarcated in milliliters. This is a milliliter graduated cylinder. So you got 10 milliliters, 20 milliliters, 30, etc. So if you needed 15 cc's, you could just go to 15 centimeters, and that would be the same thing as 15. 15 cubic centimeters is the same thing as 15 milliliters. Okay, and so that's kind of important. That's something that's not uncommon to see. This one's a little more rare. This is not so uncommon to see. So you'll actually see this in the textbook and throughout a lot of the material we do in the course. So please keep that in mind. Now, if you look at this here, we've got a three-dimensional object, right? So let's talk a little bit about some of these units of measurement real quick. If we talk about length, what are we doing? We're talking about something that's got a value in one dimension, right? So let's say I just drew a meter out. Let's say the length of this line here, of course not drawn to scale, but let's say the length of this line is a meter. Okay? That's one dimension. So we would label that as m, right? It's only got one dimension. So, and remember, in science we don't write ones. Now, what if I said, let's take a look at two dimensions. Let's take a look again at length. Here's a meter this way. And let's take a look at a meter this way. Okay? And we've got a meter this way. So now we got two dimensions. We got length and width. And what do we get there? We get area, right? Because as you measure length times width, you get area. And area, how do we represent that? That's a meter times a meter. So that's going to be a meter squared. See that 2 there? That 2 is really representing two dimensions. When we get to like this cube up here now, we'll go up here. We've got a little bit more room. You've got, let's say, length, 1 meter. You've got width, 1 meter, and you got height down this side here, 1 meter. And so if you multiply that, length times width times height, you probably remember from physical science, gives you volume, right? And so that's a meter times a meter times a meter. And so you get meter 3, or meters to the third dimension. Okay? So, why is that important? Well, it gives you volume, right? If you opened up your refrigerator and you looked at a milk carton and it was in 2 dimensions, you'd only see the front of the carton. It would really stink if you tried to pour a glass of milk out of it, because you'd have nothing behind it. You'd have no volume. You'd have no milk. You just have the front of the box. So that extra dimension, that third dimension, gives you that 3D effect. Now, how many dimensions do we experience on an everyday on an average day, right? We can see things. We see things, right? We can see length, and we can see width, and we can see height. So you can see things in 3D, okay? And that gives us perspective, okay? But there's one other dimension that we have. So we actually can experience things in 4 dimensions as human beings. And that 4th dimension that we can experience things in is time. We have a concept of time. So again, length, that's your first dimension. Width, that's length times width, 2 dimensions. And then length times width times height, 3 dimensions. And then the 4th dimension, time. So those are the 4 dimensions we live in our world, and we can sense, we can experience, and we can contemplate, and conceptually we can understand as human beings. All right, last thing, density. You all remember density, right? And the formula for density. Density is equal to mass over volume. Okay, mass over volume. So if you needed to calculate the density of something, you don't know what the density is, that's your question. Well, you could mass something, right? You could take an object, a pencil, let's say it's a pencil, and you can put it on the scale, and the scale will tell you that the pencil has a mass of 10 grams. Okay, so you write that down. Well, what's the volume of the pencil? Well, that's not so easy to get, is it? The volume of the pencil is a little bit tricky, because it's got a really irregular shape, right? It's got sides, or it's rounded, and it's long, and it's got a point and an eraser, or not, and it could be very difficult to try to just geometrically calculate that. But the easier thing to do would be to take your pencil, right, and to dip it, or to stick it into a cylinder or a beaker. So let's say you've got a beaker and you're at 50 milliliters, okay, full of water. In fact, let's make it look like water. We'll make it a little bit easier to understand here. We'll call this as 50 milliliters, and this is full of water. We got exactly 50 milliliters of water in here, okay? Pretty cool. Now we go and we take our pencil. We'll make it a yellow pencil. And we go and we put it inside of here, right? And you dip your pencil and you totally submerge it. So now you get your pencil inside the water. What's going to happen? Well, the water level is going to go up, right? Now let's say the water level goes up to here. Okay? And now you calculate, you look at that difference here, right? And you read it on the side. And the side of the graduated cylinder now says you are at 63 milliliters. You were at 50 before you put the pencil in. You submerged the pencil. Now you're at 63. So that difference there is 13 milliliters. So now you know the volume of the pencil, 13 milliliters. And this is the famous experiment that Archimedes did. You may remember him from history. Archimedes, the brilliant scientist and philosopher, and ran through the street shouting, "Eureka, I found it." That's a whole story for another day, but you can look it up on the internet if you're interested, or ask me in class and I can tell you about it. But so now we get the volume, and this was due, basically, the story goes, Archimedes discovered this process. So to calculate that density, right, it's going to be the mass, 10 grams, over the volume, 13 milliliters. And so what do you have? You have 10 divided by 13, and so that comes out to like, what, 1.3, I think, grams per milliliter. And that's your density. Quite simple. Okay? And there's some problems they gave you in the book to do and stuff, and we can take a look. And we're actually going to do some of this in class. I think we're going to do quite there's quite a few different neat things and interesting things you can do with density, and we're going to take a look at a few of them. We might do a little bit of some forensic work. We'll do some stuff with soda cans. We'll do some intuitive stuff. So you can see some of the fun and different things you can do with density. It's really quite a remarkable formula that you can do a lot of fun stuff with. Okay, so that's going to be it for this section. I hope you enjoyed it and got something out of it. And if you have any questions or we need to go over anything in class, just bring it to my attention. We'll make sure we address them. Thank you.